Thank you. So before looking into instabilities, we need to put them into a context of the solar wind. So solar wind is, generally speaking, weakly collisional plasma. And that's plasma that also expands out of the sun constantly. So there are several fundamental processes that need to live together in the same house. So first of all, this is how our measurements look like, and this is the common way to present ion measurements. These are proton measurements, all of them, in what we call a Brazil plot, because it looks kind of like country of Brazil, at least for 1 AU measurement. For 0.3 AU, it's mostly El Salvador, or pick your favorite country. But okay, Peru. So essentially, your favorite country is presented into parallel proton beta, versus the proton anisotropy realm. And this realm is good for several reasons. First of all, both of these are fairly straightforward to measure. And second, in this realm, you can plot these adiabatic expansion and also these instability thresholds, various instability thresholds. So there are several things happening at the same time. First, the wind expands. So beta increases with radial distance. So this wind is going to be, by the blue process, pushed to the right, and at some point hit the instability threshold. There is heating, and almost every heating that happens in the solar wind is preferential in certain direction. Usually in the young solar wind, it's mostly perpendicular heating, pushing this cloud up, or in the older solar wind, it's mostly parallel heating, pushing this cloud to the right. And there is actually the paper by Greg House that came out a few days ago on arXiv that gives a very nice overview of all of these mechanisms. So I'm not going to go into that. I'm just going to put some nice arrows on the plot. Also, when you hit the instability thresholds, there are instabilities that maintain this wind within the instability thresholds at least until to some extent. And finally, there are collisions, which what they do is they push this plasma towards isotropy. So if you have a stable plasma, then due to heating and or expansion, it becomes unstable. Then what instabilities do is they push it back, but not towards the local thermodynamic equilibrium, but rather towards what we call a marginally stable state. So they will act as long as the plasma is unstable towards that respective instability, and then just leave the plasma there in that state. So what happens with respect to the turbulent cascade and timescales? Well, what instabilities do is that they are able to completely bypass the turbulent cascade. How? We have this MHD, this large-scale structure, such as, for example, proton anisotropy. And then what will happen is that we will kick the kinetic instability. We'll become unstable. So because of this MHD property, which makes the plasma unstable, we'll have the ion scale extraction. And this plot on the left is an actual measurement, not a theory nor a simulation. And this is a measurement from Parker's solar probe, where you can separate the background turbulent cascade versus the ion cyclotron wave, which is given in black. And what happens is that you take the energy from large scale and then you directly push it over to ion scales, completely bypassing everything in between, on top of the background turbulent cascade that happens. And again, you get to the marginally stable state. So, on top of all that, when we calculate all this, we assume that there are no collisions in the solar wind plasma, but we know that there are. The plasma is weakly collisional, and when you take a measurement of this gradual collisional influence, so the added effect of Coulomb thermalization, which we can quantify in several ways. One that we use here is the Coulomb number, which is basically the number of Coulomb thermalization times, the collisional frequency times the propagation time. And this is, of course, dimensionless. And this is an illustration by Justin Casper that shows the ratio between alphas and protons, temperatures of alphas and protons, versus the Coulomb number and also the drift between the two populations. And what we can see is that as soon as you get into the collisionally old wind, the drift and the temperature difference disappear. So things get isotropized and completely pacified. And also, the point that I want to make, because I want to go dive directly into the linear theories, why can we use linear theories? So the Ridibe, Bandiupai, and associates have found that they compare linear and nonlinear time. So apologies for that. So nonlinear times versus the instability growth rates within the realm where the plasma is unstable, and these are wind observations. And when the plasma becomes unstable, that's actually where nonlinear times are smaller than linear times. So the background turbulent fluctuations are, in this particular part of the phase space, slower than the growth rate. So how do we reconcile the linear non-collisional theory with collisions? The answer is in time scales. Instabilities act on time scales of seconds to minutes, and collisions act on time scales of days. So before I dive into our analysis, let's go into how we obtained our data. So we look into the Helios velocity distribution functions. And on top panels, there are row velocity distribution functions, which are fitted throughout the entire mission. So there's about 1.5 million of these over 15 combined years of Helios 1 and Helios 2 observations. And they are fitted as three generally anisotropic Maxwellians. So there's proton core here, there is the proton beam, which is a secondary population here, and there are alpha particles, which here seem to be...
I'm so sorry, can I just briefly ask you to explain what is plotted versus what? I'm struggling to see the labels.
Apologies. So these are just instrument coordinates of Vx versus Vz, and in color you have the intensity of the velocity distribution. So this is the 2D reduced VDF. It's actually measured in 3D.
And the dotted line is the magnetic field direction, right?
Yes, the dotted line is the magnetic field direction. And then, because you are measuring, because the way the instrument works is that you're measuring in E over Q, so energy over charge. And what happens is that naturally these alphas get shifted as you sample them, even though in reality they are not. And therefore that's the reason we can actually distinguish the alphas from protons, even when they are not drifted in real world. And we measured a whole lot of these, and sometimes we found only core protons, sometimes we found core and beam, sometimes core and alpha particles, and sometimes all three. It could be that they are not there, it could be that our instrument cannot detect it. We actually dig deep into this to make sure that the observations are valid, but I'm going to ask you to trust me on this, and I actually can bring the discussion offline when it comes to technicalities regarding the observations. I'm just going to go straightly into the analysis. And okay, so what you do with your VDF is you have a set of parameters, which I'm going to call P. So this is your beta, your thermal speed, and then a set of VDF characteristics, density, parallel perpendicular temperature, the drift, and so on, all of which you normalize to proton core. And then you can take your favorite plasma textbook, and you can solve the dispersion relation for any given plasma mode. So every solution to this is one of the red dots, one of the plasma modes here. And then what you do next is the upgrade to traditional plasma solver, where you can plot this complex frequency.
I'm so sorry to interrupt. Okay. Can you explain what's shown on the axis?
Of course. So getting to that. So the frequency is complex. So you have the real frequency and you have the growth rate. And if the growth rate is above 0, both of these are normalized to proton cyclotron frequency. So if the growth rate is above 0, then you have the unstable mode, and then you have the wave which is generated. If the growth rate is below 0, then your wave fluctuation is getting damped. And what you can do is you can create a contour integral over the entire unstable space. If you normalize it properly, then the solution to that contour integral is going to be 2 pi times I times the number of unstable modes. And then you count and you say, okay, I have 3 unstable modes, for example. Then what you can do next is you can increase this lower level of the contour integral, and you keep increasing it until there is only 1 mode left. And that is what we call the most unstable mode, or MUM. And this is the mode that affects your system the most. So then what you can do from there is you go back to a traditional Plum plasma solver, and then you find the frequency, the growth rate, you find the propagation direction, you find all the eigenmodes, you find the power emitted or absorbed for each of the populations, so core, beam, and alpha. And you find the parameter, you can find the parameter fluctuations, and all of this is a set that I call W. So the P is VDF set, and the W is the instability set, and that's going to become important later. So we did this 1.5 million times, took us about 8 million CPU hours, and we looked to analyze it. So when you have something which is from 0.3 AU to 1 AU, which is Helios, naturally, first thing you do is you organize your results over radial distance and see what it gives. So this is exactly what we did. And we found that, okay, you might expect that more of the plasma is going to be unstable closer to the sun you are. And that is what you see. You see this is the fraction of unstable intervals, which is about 60% at 0.3 AU. And then it goes down linearly, and for the growth rates, both means and medians, the same thing goes. There's a linear decrease as you move away from the sun. And close to the sun, the core is anisotropic, so the core is the most,
I'm so sorry, I'm becoming a stand-up comedian, but can you please explain what's on the axis?
Yeah, so this is the radial distance in astronomical units from the sun.
And what about the vertical ones?
So this is just the number of observations. This is the percentage of unstable intervals. So at 0.3 AU in this data bin, we have about 60% of unstable intervals out of all of these 100,000 which are measured in this data bin. And then this is the growth rate normalized again to the cyclotron frequency. The mean for this given interval and the median for this given interval. And this is the black lines are the actual results. The red line is a linear fit. Then this is the last subplot, A5, B5, C5 show the emitting composition. So the emitting component. So is the core or the beam or the alpha the component that emits most power?
And I'm sorry, most of us are not familiar with the heliospheric physics. So we're looking at this and trying to figure out, like, zeroth order, what is going on? Can you explain in, like, very basic terms, what is the core, what is the alpha, and what is the beam? Like, just very basic, like, imagine you're talking to a high school student.
Of course. So this is the velocity distribution function.
What are these two velocities? Is this the velocity of the spacecraft, or this is the velocity of the wind, particles?
So this is the velocity as measured by the spacecraft. So basically, the way the particle analyzers work, when you mount them on a spacecraft, you go ahead and you open up a given direction, and then you sample over that direction for various values of voltage at your detector, meaning that you're going to detect the particles of various energies coming from that direction. So you do that for a given direction, then for the next one, then for the next one, then you increase the elevation, and then you do all the same thing all over again. And then ideally you cover this 2D space with various energies / velocities of particles.
So if I'm changing the direction, am I tracing out a circle here, or are there like different directions from 0, 0? or?
I think what Sasha is actually trying to ask is, so in the lower left plot there,
Yeah.
those are contour lines. This is the distribution function of ion particle velocities. If it were a Maxwellian, you would have circles, concentric circles. That's what you would have. This is, and that dotted line is the magnetic field direction. And so because the contour lines are a little extended perpendicular, that means the perpendicular temperature is larger than the parallel temperature.
Exactly.
And where that little red dot is in the lower left plot, there's a little extra number of particles there. That's like a little beam of extra ions that are moving along the field direction. And so this is a plot, and there's sort of two projections of it, of the ion distribution function. Am I explaining this right?
Yes, you are.
Okay.
And why is the top left chopped off? Is it like instrumental, or is it actual physical chop off? Like there's a line that's going at like 30 degrees to the horizontal, 20 degrees to the horizontal on the top left.
So it is instrumental, and it has to do with the field of view of the instrument and how much of actual physical space you can sample. But then you can take your fit, and what we do is they fit with a sum of three Maxwellians, one of which is proton core, the other is proton beam, and the third one is alpha.
Thank you. This is the level that I think most of the audience would probably like to hear. We would probably be lost in technical details, but this sort of basic physical picture, just like Greg described, would be extremely valuable if you could kind of give us more of that.
Of course.
And the rest of the speakers of the session as well. Thank you.
I appreciate the question, and yeah. So okay, establish that we have this velocity distribution with a given intensity for a given velocity, and this is generally the anisotropic Maxwellian, meaning the perpendicular temperature doesn't need to be equal to parallel one. And we assume that protons have two components, which is the proton core, which is the bulk of thermal particles, and the additional proton beam, the origin of which is unknown and highly debated. And there are also the alpha particles on top of that. So the entire analysis that I went through now is done considering the linear stability for a VDF, which is a combination / sum of these three components. And what you do is the growth rates of your most unstable, what you find is the growth rates of your most unstable modes and all these eigenfunctions on top of that. And then what you do next is you line them up by radial distance, because Helios was sampling from 0.3 AU to 1 AU. So you get to find that there is a linear decrease in basically instability power in the inner heliosphere as you move away from the sun. But there are more intelligent ways usually to organize your results than spatially, and you can do it by solar wind speed or by Coulomb number, which I already introduced. The gray parts are the parts where you don't trust the Helios instrument. It was built in the 70s, so it was great for the time. So if you organize your fraction of unstable intervals and your growth rates, both mean and median, with respect to the Coulomb number, you will find that there is a ceiling in very collisionally young solar wind. Basically, no collisions have affected the plasma. And over there, it is vastly unstable, and most of the intervals are vastly unstable. So there is about 85% of intervals which are unstable, and the growth rates are very large. And then as soon as the collisions kick in, you have this exponential decrease coming down to this floor, which is about 10–20% or so, is difficult to say, which says that the collisions have done their part, and now the plasma is mostly pacified, and you see that the core thermal particles, which are mostly affected by the collisions, have actually died off as the component which emits energy. Then the alphas are taking over and the beams. And how is that exactly happening? Well, this is when we actually need a machine learning. So machine learning is conveniently seen as this deus ex machina that you can apply to pretty much any problem you have, which I personally don't like. But here we really didn't have a choice. The reason being the following. We can actually estimate, if we look at our only core population. So you do stability analysis and you get this. You get your analytical thresholds for various science spectrum, mirror, parallel, fire hose, oblique, fire hose instabilities. And you see that your unstable intervals are very well confined with those thresholds. So everything which is inside here is stable. And you can kind of guess which instability is acting for which measurement. However, if there is more than one Maxwellian component, so when you add the beam and when you add the alphas, well, you cannot say anything anymore. And your eigenfunctions, so your emitted power, your fluctuations of magnetic electric field, create this 25 plus dimensional space. And you want to try to figure out, okay, what is happening? What are the instabilities which are actually being driven? So you're usually when you get a number, when you get a solution from the dispersion solver, you can look at the bunch of numbers. You can take your plasma textbook and you can infer what is the instability which is being driven there. But if there is 1.5 million of those, you cannot do it, and you cannot figure it out from 2D plots because it's 25-dimensional space and you're human.
Sorry, I'm so sorry. I'm used to seeing the lab diagram, but where the color is inside the lines. Why is the color outside the lines?
Because these are only unstable intervals. These
Okay.
are only the intervals which are unstable. And this left plot is the one where we only detected a single Maxwellian. So this is exactly what you would expect from theory, that Maxwellian is stable here and unstable there. So what did we do? And I'm going to speed this up.
Yeah, you were going to have to kind of wrap
Yeah,
things up here.
yeah. But we had questions in between. So what we do is we make this physics-informed clustering algorithm. And we called it SAVIC, Stability Analysis Vitalizing Stability Classification. So this is a chain of machine learning algorithms that do what? They, number one, do the job of the Plumage-Nyquist solver. So they do the job of the solver that solves the contour integral, and they tell you if your given distribution that you feed it in is either stable or unstable. Then they do it with certain accuracy. Then they estimate, it estimates your eigenfunctions, but then there is an extra step, which is it actually goes into the plasma physics book for you, meaning it clusters out your eigenfunctions and your growth rates and wave characteristics into physically meaningful clusters, each of which represents a given plasma instability. And aside from the fact that it can do instead of you, it's actually insanely fast. So I mentioned there was 8 million CPU hours to produce Helios, to process the Helios data set. With SAVIC, you do it in about 7 seconds. And the arbitrary large number of observed or synthesized intervals can be processed very quickly.
Okay, I'm going to have to kind of jump to the conclusions here. We're
Okay.
really out of time.
Okay, so 30 seconds on this slide and I'm done. So you can actually label every single instability that you have here. And these are the bluish ones are the core instabilities, and in the young wind they dominate. Then in the older wind you have this various types of alpha instabilities which are greenish. In the older solar wind you also have some parallel and oblique fire hose, and then you find that the beam type instabilities don't care about the collisions and they just live on top of the other components over there. So I am not going to dive into the quirks of various beam instabilities. I'm going to skip all this. I was going to say that in the young wind, there is actually the core anisotropy and various core modes that are dictating the solar wind dynamics. In the older one, there are alphas. There is the proton beam that lives in behind all that as a separate population and doesn't feel the collisions. There is a Python package that can be used for people who want to try SAVIC on their own. It's actually very simple to use. And I'm going to leave you with a bunch of QR codes that are going to lead you to a bunch of references, online softwares, and Python packages.
Thank you.
Thank you.
Okay, do we have any more questions, since we had plenty during that talk?
This is,
I'm trying to see patterns.
yeah, this is very isotropic pattern, I'd say.
Go ahead, Sasha.
So first, I wanted to thank you for your patience in answering my really naive questions. I'm sorry for taking up the extra time. So I wanted to kind of take a step back and ask, what is the big picture of what we learned from this? So we have the core, which is, I guess, Maxwellian that shifted in velocity relative to velocity of the spacecraft. We have the beam that's not the beam. We have the other component that's
the beam which is shifted with respect to the core.
Shifted with respect to the core. And then you have the sort of anisotropy. So what I was confused is I thought that, you know, the instabilities would be saturating, like limiting the degree of anisotropy. So I would have expected that the core would be mostly stable. So why are there instabilities in the sort of thermal core? And why are you focusing on that as opposed to like understanding the degree of anisotropy of the things that are actually anisotropic?
Well, the core itself is very anisotropic in the young wind. So it lives over here. And this is the anisotropy of the entire population, not only the core. So this is 1, and this is T perp larger than T parallel. And the core itself drives this anisotropy to be very large because there is strong perpendicular heating in the young wind. And the answer to the question that you initially posed is we want to understand what are the drivers or various drivers of free energy within the velocity distribution as the solar wind expands, and how those drivers create the shape of the distribution as is, and how the instabilities react back to number 1, revert some of that work and get the plasma to a certain marginally stable shape. And number 2, how much energy, because when you inject energy into particles when you heat, how much energy is sent right back into waves via linear instabilities. And that you can actually go ahead, I didn't get to it, go ahead and quantify how much energy is thrown back into instability. So when you quantify the solar wind heating, there is the backleash effect that also needs to be quantified in order to get a net transfer of energy from turbulence into solar wind particles.
Thank you.
Just to add on to that, this kind of analysis is one of the ways that we can try to answer the question that Trevor posed at the very end of saying, where do those waves come from? Well, this is one possibility, having these large anisotropies at the core. Is that going to be the right source of free energy that will actually drive the waves that Trevor and many other people have observed? So that's another addition to that.
So I have one question for you, and relative. So as you've said, these instabilities can generate fluctuations, which then contributes to part of the turbulence, but they also have to be generated by something. So based on your analysis, what is your thought about what is the source, the primary source of these instabilities? Do you think that it is more to do with turbulent heating or more to do with expansion in the solar wind?
Well, it is certainly both. The price question is to what extent which process is represented there. So we do know that deeply in the corona, there is very strong preferential perpendicular heating. This is our starting point. We have no idea where the beams are coming from. There are several theories on that. But generally speaking, we need to assume that in this first stage of the solar wind development, where the alpha speeds are very large, the betas are very low, and the wind is very anisotropic, there is a very, both linearly and perhaps non-linearly unstable plasma that is acting out and that creates this starting setup for the place where we actually start measuring it. So by the time we actually get to see the plasma and get to sample it, it is unstable to a given extent in both terms of the core, which is probably perpendicularly heated close to the sun, and then survives as it survives to the extent that instabilities allow it to survive as the solar wind expands. And also there are these insane beams which are also that have the perhaps non-Maxwellian constructions which are in the beams, which also become unstable in the process and which dissipate as the instabilities allow.
Okay, thank you.
That was addressing your question.